Very important topic. Okay, difference equations and the transform. Repeat again, very important topic in digital signal processing. Okay, here in the first line we see a difference equation. Here A0 is equal to 1, y of n is equal to sigma k from 0 up to capital M, bk times x of n minus k, the terms related to input, b0 x of n, b1 x of n minus 1, blah blah. Okay, this part was in this left hand side, but we have moved everything to find what's the output. Okay, so they have moved from left side up to right hand side of the equation. So taking minus. Okay, minus sigma k from 1, because A0 has appeared here, so the index should start from 1, k from 1 up to capital N, ak times y of n minus k. A general difference equation up to degree of what you are seeing. Y of z, okay, we are taking z transform. We earlier we noticed that a delay, a shift in time domain will be z to the power of minus the same delay. So we will have y of z summation bk x n minus k, so it will be z minus k x of z minus, again similar topic for the second part, which will lead to finding the transfer function. H of z will be equal to y of z over x of z, and it will be equal to summation related to the input terms over 1 plus terms related to the output or feedback parts. These parts are feed forward, these parts are called feedback. Anyhow, H of z, and what about frequency response? The same discussion. So if we have difference equation, we will find very easily H of z and H of omega. Or vice versa. If we have transfer function, we should be able to reach to the difference equation. It needs some practice. Proposition 3.6. Find the system's transfer function, frequency response, and DFT in the following difference equation. If you are able to understand what's happening, so you have started learning very important part of DSP. Okay, y of n is equal to 2x of n minus 1.8 x of n minus 1 plus 0.36 x of n minus 2 plus 0.325 y of n minus 1 minus 0.0187 times y of n minus 2. Solution. System transfer function will be, you see, just finding by looking at the difference equation. 2, 2, minus 1.8, minus 1.8, z minus 1. 2 delays. So, plus 0.36 z minus 2. So you should be able to find the h of z by looking. It takes 2 seconds. What about the denominator? It's related to the terms of the output, so it will be 1 minus 0.325 z minus 1, again minus will be plus 0.0187 times z to the power of minus 2. Okay, just imagine if we had another terms n minus 3 for input and output, what would be the result? Okay, and frequency response very easily. Everywhere you see z, just substitute it with e to the power of j omega. Minus 1 minus j omega. Minus 2 minus j2 omega. And that's it. So you need only to look at it. Now, difference equation will have such a result. Amplitude of DFT and frequency response. You see, they are both similar, and we will prove it inside Python environment. Figs 3.13 and 14 show the amplitude and phase of DFT and frequency response of the corresponding difference equation. Let's have a look to the phase. Again, similar result. Now the Python, the program FFT, okay. Let's run it. Figure 1 and figure 2. We had screen grab of the program after running. What have we written here very quickly? Numerator 2 minus 1.8 and 0.36. What about denominator? 1 and minus 0.325 and 0.0187. In FFT 512, FS 1000, finding FFT numerator, MP numpy, FFT, using FFT for numerator, using FFT for denominator, dividing numerator over denominator. Here, H1 imaginary part, H1 real part, the fraction. What about the phase? Here we compute the phase from here up to here based on the equation, arctangent, and converting it back to degree instead of radian. And now here we compute the results directly for frequency response. So we define omega, linear space from 0 up to 2 pi, taking an FFT samples, and providing environment for absolute value of H2 and phase. Okay? Using a while loop, you see, we have written Python code from scratch. We try not to use the advanced libraries because generating programs from scratch will result in self-confidence, and that's very important. Okay? That's our morality in this course. Now, computing very simple relations based on the equation we have and plotting the results. Okay, let's go back to the lecture note. The same coding here. You will have access to them. Now, questions. Try another difference equations up to 10. Then you will learn the idea. Write the syntax as functions being called by the main program. Which method do you prefer to use later in your designs, FFT-based or frequency response-based? I myself prefer FFT-based solution. Anyhow, both will have the same results. We proved it. Next question. Study the role of NFFT in the program by starting from small values up to large ones. Say it's 32 up to 2048. Or any multiple of 2. And make a report about it. You should have a discussion. Present the amplitude in dB 20 times log 10 of abs of z. Okay? Define the type of the system. Is it low pass, high pass, band pass, or band stop filter, or none of them? Okay? Now, the next topic. Analysis of feedback systems using Z-transform. Here you see a discrete feedback system, input, error signal, passing through the first system with impulse response of h of n, leading to output. Output has a feedback passing through the second system h2 of n, leading to w of n, and subtracting w from input. We mentioned error signal. Okay. Now we want to use Z-transform to solve the problem. The above figure illustrates a digital system with feedback where y of n is equal to error of n or e of n convolved with h of 1. Error is equal to input x of n minus w of n, and w of n is equal to y of n output convolved with h2 of n. The analysis in time domain is more complicated, but using the Z-transform, typing mistake, sorry, we have y of z being equal to e of z h1 ez xz minus w yz times h2. So yz will be x minus w times h1, which will lead to having h of z being equal to y of z over x of z, and being equal to h1 of z over 1 plus h1 of z times h2 of z. So everything